Hi, I'm Dave LaJack. I'm an exploration geologist and a professional prospector. I've worked from the Arctic of Alaska down to the deserts of Mexico. In fact, I earn my living by making lode mineral discoveries and leasing the claims to mining companies. There's pretty good money in it, but it helps if you know what you're doing. You know, there's a common misconception out there that mines are found by big mining company geologists who just look at infrared satellite photos and say drill here, and that all the mines have already been found, there's nothing left to discover. Well, that's not the way it is. Actually, mineral discoveries are made by people out walking the ground, taking samples. In fact, you don't even have to be a professional geologist to be a good prospector and find great prospects. Some of the biggest mineral discoveries in the last 20 years have been made by individual prospectors taking samples. So what I'm going to show you are the techniques and the methods exploration geologists and professional prospectors use to make the discoveries that make the mines. So whether you do this full-time or just in your spare time, knowing what to do and just how to do it will greatly increase your chances of becoming a mine finder. You know, I heard an old-timer in the Yukon say once that when you make a valuable discovery and it's all yours, it's a powerful feeling. Well, he was right. So come on, let's go back to the office and get started. To begin, I suppose I should define what prospecting is. Prospecting is the systematic and scientific search for ore deposits. Systematic and scientific in that you have a well-thought-out plan and you use proven techniques. An ore deposit is any concentration of minerals that can be mined at a profit. The commodity mine can be metallic like gold, silver, copper, or zinc. It can be gemstones like diamonds, or even sand and gravel. However, in this tape series, we're going to focus on metallic minerals. But before we get going further, I'd like to introduce John Duncan. John has a master's degree in economic geology. He's worked as a consultant in the mineral exploration business for years. In fact, John and I have worked together off and on various prospecting ventures over the years. So before going further, or before we go out into the field, John's going to give us a basic lesson in geology and ore deposits.
Ore deposits are geologic features, which means that they form by normal geologic processes. This doesn't mean that they're common or easy to find. It just means that they don't occur at random. Ore deposits form in and along with the rocks that make up the crust of the earth, and they're formed by the same geologic processes. By geologic processes, we mean things like volcanic eruptions, earthquakes, and floods, which you're all familiar with. Geologists understand these things pretty well, and all these processes can contribute to the formation of mineral deposits. The point is that there are patterns to the occurrence of ore deposits, and at least to some degree they occur where they should be expected to occur. With this in mind, it's important that the serious prospector have a working knowledge of geology. This video is too short to teach a course in geology, so you'll need to buy or borrow a beginning textbook in geology and read it. But as an introduction, we'll go over some basic geologic concepts and terminology to get you started. The rocks that make up the crust of the earth fall into two broad categories, igneous and sedimentary. Igneous rocks form by cooling from a molten state, and they occur in two basic types, volcanic and intrusive. Volcanic rocks are formed from lava that actually reaches the surface of the earth. Lava erupts from volcanic vents and blankets the surrounding ground. As it cools and hardens, it becomes volcanic rock, which is generally seen in horizontal layers or irregular piles. Intrusive rocks form from molten rock that never reaches the surface. This molten rock is called magma. It intrudes or is injected from depth in the earth into shallower, cooler levels of the crust, where it cools and solidifies without reaching the surface. Intrusive rocks are exemplified by granite, which forms at relatively great depths, but also include rocks of many forms and compositions that form at different levels in the crust. We refer to a body of intrusive rocks as an intrusion. A regular blob-shaped intrusion is called a stock. A narrow, tabular intrusion is called a dike if it's oriented approximately vertically, and a sill if it's injected horizontally between rock layers. Some of the more important intrusive rocks to the prospector are those that form at relatively shallow depth, often within or below volcanoes. The second broad category of rocks is sedimentary rocks. This group of rocks is deposited from water and includes familiar types like limestone, shale, and sandstone. These rocks are derived from older rocks that have been weathered and eroded at the Earth's surface. They are deposited by rivers, streams, lakes, and oceans as sediments, such as silt and sand, and eventually harden into rock. After rocks are originally formed, they're commonly subjected to conditions which change them in one way or another. Simple burial and compaction cause soft sediments to turn into hard sedimentary rocks. If rocks are buried more deeply within the earth, the heat and pressure can change them dramatically. Metamorphic rocks are just sedimentary or igneous rocks that have been subjected to high temperatures and pressures, and as a result have been changed or metamorphosed into rocks of different character and appearance. Pressures within the earth can also cause rocks to be bent and folded, so that originally planar horizontal beds are twisted and distorted. Other pressure conditions can cause rocks to break and the resulting pieces to move against each other along faults. All rocks are made up of minerals. A mineral is a specific combination of elements which come together as atoms and arrange themselves into a specific three-dimensional structure. So every different mineral has a specific composition and unique physical characteristics. Minerals form mainly by crystallizing out of magma or lava as it cools, in the same way that ice crystals form in water as it cools. They can also crystallize or precipitate out of water that contains dissolved minerals. Let a pan of salt water evaporate to see this happen. The most common minerals are made up of common elements like silicon, oxygen, hydrogen, sodium, and potassium. These elements form minerals such as quartz, feldspar, and mica that make up the bulk of most rocks. The less common elements, including metals such as gold, silver, copper, zinc, and others, occur as less common minerals. It is unusual concentrations of these minerals that result in the ore deposits that we prospectors search for. Important ore deposits occur in all major rock types, and they form by the same processes that form rocks. Placer deposits are one type of deposit that is formed by simple sedimentary processes. I'm sure you've heard of the many placer gold deposits, such as those in the Mother Lode country of California and the Yukon of Canada. But any mineral that is relatively dense and durable, including gemstones and platinum, can form placer ore deposits. Some ore deposits also form by igneous processes. They crystallize directly from magma. Most of the world's platinum, and essentially all of the world's chromium, come from very large intrusions from which these metals were segregated before the magma cooled and hardened. The most important broad category of ore deposits to the Hardrock Prospector, and the type that we will concentrate on here, is the hydrothermal deposit. Hydrothermal, if you remember your high school Greek, means of or pertaining to hot water. Hydrothermal ores are deposited into or onto their host rocks by the actions of hot water. This can be thought of as a metamorphic process in which the heat and the dissolved chemical content of the hot water or hydrothermal fluid change the host rock from plain old rock into a valuable ore deposit. More specifically, hydrothermal fluids, which are commonly quite acidic and saline, are able to dissolve mineral constituents, including metals. They can then transport the minerals in solution to a point that they are deposited as hydrothermal mineral deposits. Important factors such as the source of the water, the source of the dissolved minerals, and the mechanism of deposition or precipitation can be almost infinitely varied. The important thing to remember is that hydrothermal mineral deposits are formed as hot, mineral-rich fluids encounter conditions that cause them to deposit their contained metals. Under the right conditions, hydrothermal systems can concentrate metals by scavenging them from a large volume of rock or magma and then depositing them into a relatively small volume of rock, the ore deposit. Hydrothermal mineral deposits come in many varieties, but they can be classified into a few broad categories. We'll discuss 5 categories of mineral deposits here. Once again, if you're serious, you should buy or borrow a textbook on economic geology and study it carefully. We can cover only a fraction of the material here. The 5 classes of ore deposits that we'll discuss are porphyry or intrusion-centered deposits, mesothermal quartz gold veins, carbonate replacement and Carlin-type deposits, epithermal and hot springs deposits, and volcanogenic massive sulfide deposits. Porphyry or intrusion-centered deposits are classified by their relationship to an igneous intrusion. The term porphyry describes an igneous texture in which relatively large crystals float in or are surrounded by ground mass of finer-grained material. The intrusions associated with this type of deposit commonly have this texture, hence the name porphyry deposit. Porphyry copper deposits are the most well-known example of this type. They are common here in southern Arizona and in many areas of the world, and they are the most important source of the world's copper production. Other important varieties of porphyry deposits include porphyry molybdenum deposits, which produce essentially all of the world's moly, and intrusion-centered gold deposits, which have gotten a lot of attention in the last few years. The common feature of all these deposits is an intrusion at or near the center, which was instrumental in the deposit's formation. The ore can be within the intrusive rock, or in the surrounding country rock, or more commonly in both. Mesothermal quartz gold veins are what we think of as the classic mother lode type vein. A vein is just a tabular or sheet-like body of hydrothermal minerals, typically contained within a fault or other crack in the rock. Mesothermal is just a big word that means formed at medium depth and temperature. The important common characteristics of these deposits are large, continuous quartz veins localized by large faults or breaks within metamorphic rocks. The rocks that host the veins are generally of low metamorphic grade, which means that they haven't been cooked up too hot. These rocks are typically near large intrusions or high-grade metamorphic rocks which have reached high temperatures. Mesothermal quartz lodes are important sources of gold, as in the Mother Lode District of California and the gold fields of eastern Canada. These deposits formed when a large intrusion or other regional heat source caused the heating and metamorphosis of surrounding rocks. As this happened, the heat and mineralogical changes in the rock drove off contained water. This water, along with its dissolved minerals, then moved through the rock away from the heat source until the combination of cooler temperatures and a large fault to concentrate flow provided the right conditions for fluids to deposit their mineral lodes as gold-bearing quartz veins. Carbonate replacement sulfide deposits and Carlin-type gold deposits are actually two important deposit types that have been lumped together into one category for this discussion. Carbonate replacement deposits are made of massive lead, zinc, and iron sulfide minerals that have replaced limestone or similar sedimentary rock. Limestone is made up of calcium carbonate, so it and similar rocks are known as carbonate rocks. Sulfides are an important class of ore minerals made up of metal and sulfur. Carbonate replacement sulfide deposits form important ores of lead, zinc, and silver. Carlin-type deposits are disseminated gold deposits hosted by carbonate rocks or other sedimentary rocks such as shales or sandstones that are also rich in carbonate. It is Carlin deposits, named after a small town near Elko in northern Nevada, that have made the state of Nevada one of the most important gold-producing regions in the world. Although these two deposit types are distinct in appearance and metal content, they have important similarities. They are both hosted by carbonates or carbonate-rich sedimentary rocks, and they are both thought to be related to intrusive rocks. They form when acidic, metal-bearing hydrothermal fluids come into contact with carbonate. The acidic waters react with and dissolve the carbonate, and in the process neutralize themselves. This causes them to drop their load of dissolved minerals. The ore deposits are not veins, but are typically irregular bodies whose shapes are controlled at least in part by the bedding of the host sedimentary rocks. Epithermal and hot springs type precious metals deposits are formed at shallow depths within active volcanic systems. They form sometimes very rich veins of gold and silver and less important lead and zinc. Many of the famous mining boom towns of the western U.S. were developed on epithermal bonanzas. Examples include Cripple Creek, Colorado, and Virginia City, Nevada. The deposits are commonly hosted by veins or breccias, masses of shattered rock fragments cemented by a matrix of hydrothermal minerals. Their textures indicate that the ore minerals filled open spaces such as cracks and cavities in the host rock. The host rocks are almost always volcanic rocks or closely associated shallow intrusions. Metals are deposited when the hydrothermal fluids boil as they approach the surface of the earth and the confining pressures are reduced. The depressurization and boiling are often violently explosive events that cause rapid changes in fluid chemistry and dissolved mineral concentration, and thus rapid deposition of minerals. Epithermal deposits grade upward into hot springs deposits, which are formed at or very near the surface of the earth. Hot springs deposits are generally mined for gold and silver, but are also important sources of mercury, and they can carry large and sometimes troublesome amounts of arsenic. These systems are exemplified by the active hot springs and geysers in Yellowstone National Park and other active volcanic systems around the world. The thermal waters of Yellowstone carry large amounts of mercury and arsenic, as well as significant gold. There are almost certainly precious metals deposits being formed right now not far beneath the surface at Yellowstone. Volcanogenic massive sulfide deposits are the last major category of deposits that we'll discuss. These deposits are essentially hot springs deposits that form on the sea floor. And similar to other hot springs deposits, they form in close proximity to, in this case, subsea volcanic activity and are hosted by volcanic rocks. Recent submarine exploration has revealed these deposits in the process of forming. They've been labeled black smokers because metal sulfides precipitate in a cloud of black smoke as the metal-rich hydrothermal fluids mix with cold seawater when they issue from the seafloor hot springs. These sulfide clouds rapidly settle out of the water and pile up around the vents. Eventually, large deposits of iron, copper, zinc, and lead sulfides, commonly enriched with silver and gold, accumulate on the ocean floor around these hot springs. Volcanogenic massive sulfide deposits are important sources of both base and precious metals. They occur in many parts of the world where old volcanic seafloors are now exposed on dry land. When hydrothermal deposits form, they don't just deposit the metals that we're looking for, they also deposit a lot of other minerals as well. Remember, even a high-grade vein is mostly quartz, not gold. Hydrothermal systems deposit many more non-ore minerals than ore minerals, and they react chemically with and alter their host rocks. This alteration involves much more rock than the ore deposit itself, and is normally easier to see than the actual ore mineralization. So it's important that you be able to recognize alteration when you see it. We'll go over this in more detail when we're out in the field.
Before you begin any mineral exploration program or prospecting trip, you need some sort of plan that'll get you to a discovery. The plan should proceed logically from one step to the next. First, you need an idea. Then you need to do enough library research to refine your plan to a deposit type and a general target area. Research the land status to get it down to a specific area, then plan your fieldwork. So let's get started with an idea. There are ore deposits all over North America and the world. For instance, in Nevada you have disseminated Carlin-type gold deposits. Down in Arizona are the world-class porphyry copper deposits. Up in the Canadian Shield of Ontario and Quebec are mesothermal gold lodes and massive sulfide deposits of base and precious metals. And even in Tennessee, there are zinc deposits. To begin then, you need to decide what mineral or minerals you want to look for, like gold or copper. This decision will depend on the markets for the various commodities, what you're likely to find in your area, and just what you're interested in. Once you've decided on the commodity, it's also good to have an idea of the ore deposit type and the basic geology of the area to be explored. For instance, you wouldn't be looking for a mesothermal gold lode in the carbonate lead-zinc districts of Missouri. The next step is library research. This can be done at any major university library or a U.S. Geological Survey or State Geological Survey office. These facilities have tons of published and unpublished articles and maps on geology, geochemistry, and geophysics for the U.S. and other parts of the world. The people that have put together these reports have already spent a lot of time in these areas and can save you a lot of legwork. A lot of useful information can be gleaned from their reports and maps. Don't be afraid to ask the geologists questions. Most are more than willing to help you by answering questions for anything they know. An important thing to research is the prospecting or mining history of an area. I found old USGS bulletins extremely helpful because one of the best places to go looking is where the mineral that you're seeking has already been found before. Knowing where the old-timers worked or where something has already been discovered or mined is a real plus. So don't waste a lot of time and money by running off to some area just because your drinking buddy had a dream that there's a whole lot of gold somewhere. Science doesn't have all the answers, but it's funny, the more you know, the luckier you'll be. I can't emphasize enough the importance of spending time in the library, researching the area to be explored. Don't go before you know. If you don't have a pretty specific idea to start out, you'll begin your library work by going through the most general materials first. Start with a map of known deposits and occurrences and a geologic map. Looking near known mines or prospects is a good idea as long as there is open ground. If there's open ground near a large operating mine, it's probably already been explored carefully, but prospecting around smaller old mines and prospects is recommended. The old-timers didn't find everything. From there, go to the geologic map. Look at the geology of the areas with known deposits and see if there are areas with similar geology that might contain similar ore deposits. Rocks of the same age and type or faults that host known deposits and extend in open ground are good places to start.
If you decide to prospect an area without known mineral deposits, it's important to pick an area with favorable geologic characteristics. As we know by now, for a hydrothermal deposit to form, A heat source is a primary requirement. This usually means an intrusion. So if you're trying to decide where to go looking, an area with intrusions is a good place to start. Felsic to intermediate compositions are much more interesting than mafic rocks. And generally, relatively small and shallowly emplaced intrusions are more prospective than very large and deeply emplaced ones. Volcanic rocks are not generally prospective unless they have associated intrusions. Areas near these intrusions, even if they are only small dikes, can be very prospective. Also, major faults are a good place to prospect. Faults provide pathways for hydrothermal fluids and in some cases intrusions to move through the rocks, so they are places that mineral deposits are likely to form. In general, the more complicated the geology, the better. If a fault is good, several faults are better, and fault intersections are better yet. Multiple intrusions are better than one.
Now remember, these are just very general guidelines and there are always exceptions to the rules, so go with whatever leads you feel are important. Once you've decided on an area to prospect, the next thing to do is check out the land status. Land status simply means who owns the surface rights and who owns the mineral rights. The reason for knowing this is so that you don't trespass on someone else's private ground or trespass on someone else's mineral rights. Besides breaking the law by trespassing and risking your own personal safety, nothing could be worse than actually making a lode discovery and then not being able to acquire the mineral rights after you've just spent a lot of time, money, and effort on the project. Land status determination isn't hard to do, but it must be thorough. The first step is to determine what land is public and what land is private. This can be done by visiting a Bureau of Land Management office. The BLM is an agency of the U.S. federal government. Remember that the people working there are there to assist you, so don't be afraid to ask them for help. At the BLM office, there'll be maps like these which show general land ownership. They're easy to read because they're color-coded. These maps are also available in larger scales when you want to get down to the details. Keep in mind that the owner of the surface may be different than the owner of the subsurface, which means the minerals. As a rule, if the mineral rights are public, you can prospect that ground even if the surface is private. You just have to respect the surface owner's interests. Even if the federal or state government controls the mineral rights, it doesn't necessarily follow that it's open to prospecting. Although west of the Mississippi River, BLM ground and National Forest ground can generally be staked. East of the Mississippi, federal minerals must be leased. And national parks, monuments, preserves, and wilderness areas are entirely closed to mineral entry. Another place to find land status maps or information is at a Geological Survey office or a State Land Department office for the state in which you're interested. These offices are usually found in the state's capital. Once you've determined that the area that you're interested in is open to mineral location, it now becomes necessary to check and see if there are any valid existing claims in the area. Claims give the owner the right to explore for and develop locatable minerals, metals, and precious stones. This doesn't include the non-locatable, leasable minerals such as oil, gas, sand and gravel, and certain other minerals. Researching claims on federal ground is done at two places, the BLM office and the county recorder's office. At the BLM office, claims are recorded on microfiche and also on computer files. Claims on microfiche are listed by owner's name, by legal description, and also by claim name. Again, don't be afraid to ask for assistance. That's what the folks in the office are there for. The county recorder's office is generally found in the county courthouse. Here, the claims may be on microfiche, listed on a computer, or you may actually have to search the books, which is quite time-consuming. Ideally, the area that you're interested in will be wide open. However, if there's very little unclaimed ground in the area, you might not want to bother with it. If access to your prospect area is blocked by other claims, that's okay. Claim owners don't own the surface rights. You can drive over or walk over someone else's claims. You just can't prospect there without their permission. So be careful, some people can get nasty. To check land status, you'll need to visit the state land office for the state in which you're planning to work. Different states have different procedures. Just ask someone in the office for help. Finally, remember that private land is just that. Always get permission before going on someone else's property. It may keep you from being shot or arrested for trespass. Once you've decided on a commodity and an area to explore, you'll need a method to evaluate the mineral potential of the area quickly, effectively, and economically, eliminating some areas and identifying others for follow-up work. This is the role of exploration geochemistry. Geochemistry refers to the chemistry of the earth. In the simplest sense, mineral deposits are just unusual concentrations of certain chemical elements. These elements include the ore metals, such as gold and silver, as well as other elements that tend to be associated with the ore, such as arsenic, antimony, and selenium. Geochemical prospecting involves a systematic sampling of these elements in the hope that they'll lead you to a deposit. If a mineral deposit is exposed to weathering and erosion, the high levels of metals and other elements will be dispersed in the soils and eventually into the sediments of the stream that drains the deposit. This process creates an area of higher than normal geochemistry that is much larger than the mineral deposit itself and is a bigger target for the prospector. Systematic geochemical sampling allows you to sniff out or see these potentially interesting areas which might otherwise go unnoticed. The higher the normal concentrations of metals or other elements in the sediments or soils are known as geochemical anomalies. Anomaly is a statistical term that simply means out of the ordinary. So geochemical anomalies are defined in relation to what is normal for the material being sampled. This normal value is referred to as the background value. Generally, 2 or 3 times background is called the threshold value, and any value above the threshold is considered anomalous. For example, in stream sediment samples, most values for gold will be less than 5 parts per billion, or ppb. Using 5 ppb as background, the threshold value might be 10 ppb, so anything above 10 ppb should be considered anomalous. In a large sample set, you may find that within your population of anomalous samples there is a smaller, much more anomalous group. These are the ones worth following up. In theory, the closer the sample is collected to the original source of the anomaly, the higher the concentration of metals will be found in the sample. This principle allows the prospector to trace his way back to the source of the anomaly and with thoughtful interpretation decide where to take soil samples, trench to bedrock, or even drill a hole in order to make a lode discovery. All right, we're ready to head out in the field. The first thing to do is get all of our gear together. We'll need all the basic outdoor gear, which includes a good hat, good boots, sunscreen, plenty of water, in some places, bug dope or even bear repellent. We'll also need prospecting supplies and equipment. Maps are very important. 7.5-minute topographic quads are the best. They're available from the USGS and at most outdoor and hiking stores. We'll need a compass, rock hammer, some sample bags, both plastic Ziplocs and cloth, flagging or metal tags, waterproof markers for labeling the bags, some kind of field pack, notebook or clipboard, pencil and pen, round point shovel, gold pan, string box or tape. Most of this stuff can be obtained from Walmart, but for a few things you might have to go to a specialty outlet. Finally, it's a good idea to tell someone where you're going and when you expect to be back. It's best to be safe. No amount of gold is worth losing your life over. As we've mentioned, one of the best ways to evaluate large areas is by sampling stream sediments. Stream sediments are made up of material which has been eroded from bedrock and carried downstream. In theory, if mineralized bedrock within the stream's drainage has been eroded, the sediments will contain a higher concentration of the metals than sediments from a drainage with no mineralized bedrock. Also, metal concentrations should increase upstream as the lode source is approached. So, if there's a deposit to be found in your area of interest and you sample that area adequately, one or more of your samples should contain anomalous metal values. This will immediately tell you to focus your prospecting efforts on the stream drainage or cluster of streams giving the anomalous values. By this method, you've eliminated large areas quickly without having to cover every inch of the barren area. Distances between sample locations may vary, but generally they're on the order of 1/4 mile. For reconnaissance purposes, it's best to sample all the important tributaries in a drainage. And also remember to mark on your map as accurately as possible your sample locations. It doesn't do any good to have great results and not know where they came from. There are 3 basic techniques for collecting stream sediments that are commonly used: pan concentrates, 80 mesh, and silt sampling. The -80 mesh method is the most widely used and standard method. It's the technique you'll use most. Pan cons are used mainly for sampling large drainages and are useful for quick visual identification of heavy minerals like gold. The silt sampling method is designed to detect very fine-grained gold that might escape the pan or be diluted by the coarse material. Sediments are segregated by size using screens. The mesh size of the screens is measured in holes per linear inch. So an 80 mesh screen has 80 holes per inch, and a -80 mesh material is the fine fraction that will pass through an 80 mesh screen. The minus 80 mesh fraction is the size fraction that is usually collected in the standard stream sediment sampling program. This fraction will collect not only the primary minerals, but also metal ions that have bonded onto clay and silt particles. In practice, the lab will do all the screening. All you have to do is take the sample. Collect your sample from the active part of the stream. Fill the bag with your material, picking out some of the bigger rocks that are unnecessary. Be sure that you have at least a half a cup of material that would pass through an 80 mesh screen. You can squeeze out some of the extra water. Actually, these olefin bags are great because they're porous and helps you get rid of some of the extra water and makes your carrying weight a little bit less. Panning your sample allows you to concentrate the heavy minerals that are commonly associated with mineral deposits and thereby strengthen an anomaly that might otherwise be diluted by the light fraction. Native metals such as gold and platinum, sulfides and other heavy minerals that are resistant to destruction are easily concentrated using a gold pan because of their high densities. Anomalous amounts of these minerals can be identified visually or by laboratory analysis. In collecting pan cons, take your samples from areas where you'd expect natural placer accumulations, such as inside bends of creeks, behind boulders, or any other obstruction to stream flow. Fill your pan. Once you've filled your pan with your material, look for a comfortable spot to pan it out. It's generally where the water flow isn't so great. It's calmer water. To begin the panning process, get everything wet, completely under the water. Break up any clay particles that might be in there, and don't throw anything out until you've completely washed it off, like sticks or bigger rocks, because the heavy concentrate minerals might be stuck onto those, and if you throw those things out before you've completely washed them off, you could be throwing away some of your concentrate. So once you've completely gotten everything wet and the clay particles are broken up and you've thrown out some of the bigger rocks, you can begin the panning process, and basically it's just agitating the pan either by a circular motion like this or the old steering wheel method. Once you've shaken it up enough, you tip the pan forward slightly and just begin a gentle dipping motion. The lighter material begins to work its way out the front of the pan. The heavier material stays behind. After you've done that about a half a dozen times, tilt the pan back, level, wash everything back into the center of the pan. Don't wash anything without it being completely underwater. Because if you start washing it out like this, you could be throwing away gold or other heavy minerals that are stuck to these rocks here, or this material. So be sure when you're washing, it's always underneath the water. And again, you just repeat the process, letting the water come into the pan, tipping the pan forward, and the lighter material is moving out. It's okay to rake material out, but again, you want to do it so that it's underwater. It's a real simple motion. You don't really have to throw the material out. The water will do it for you. And when taking your pan con, you want to pan it down to the first site of black sand. And that's about 1/3 of a cup of material. You want to have enough material so that the labs can have some stuff to work with. Okay, I'm starting to get down to the heavies now. A couple more times like that and we'll have it. Okay, that's probably pretty good. I'm starting to see a fair amount of black sand in the corners. Again, you can pick out some of the bigger rocks, the bigger stones, but make sure the pan and the material are completely wet. Now all you want to do is just bag this material. Get out your bag, tip it forward. You want to be careful at this stage that you get everything. And there you go. That's your pan concentrate sample. Silt sampling is the third method of stream sediment sampling. By collecting the fine fraction, generally -200 mesh or finer, it's possible to recognize anomalous amounts of metals that might otherwise go unnoticed because of dilution from the coarser fraction. Basically, you just take a shovel full of this fine silty material, or you can even use your hand in some cases. You can see how fine and silty that material is. Now you just fill a bag. Again, you want enough material so that the lab will have a sufficient sample size. That's probably enough material right there for a good silt sample. Oh yeah, when you're in the creek, keep an eye out for mineralized pieces of rock like quartz veins. Sometimes this material, which is called float, can be traced right back to its original lode source. Save yourself a lot of trouble. Okay, you started with a large area, and by stream sediment sampling, you've narrowed the search down to one or a cluster of drainages that are giving you anomalous geochemical values. Now you still may be looking at an area of several square miles in which to prospect for the lode. Logically, the lode must be at or upstream from your last anomalous stream sediment sample, since the sediments can't have come from downstream. If you have several drainages that form a cluster of anomalous samples, then the target must be situated somewhere between them. The next step, assuming that there isn't any rock cropping out in your target area, is to collect soil samples. This is normally done in a grid pattern. Ideally, your grid should be big enough to cover the target area and tightly spaced enough that your samples won't straddle the deposit. If possible, the traverses should be oriented perpendicular to the long axis of the suspected deposit. The spacing of samples and traverses depends on the type and size of the deposit being sought. Ideally, the traverses should be spaced at intervals not greater than 1/3 the expected length of the deposit, so that at least 2 lines will cross the anomaly. Smaller targets, such as vein gold deposits, will require a tighter, closer sample spacing than a larger target, such as a porphyry copper deposit. Generally speaking, if you have a small budget, a grid with traverses 400 feet apart and samples collected every 200 feet is a reasonable pattern to start with. Obviously, the tighter the pattern, the more it will cost, but the more information you'll have. When you're ready to begin taking a soil sample, there are a couple things that you should be aware of. As a general rule, soil sampling works in areas where the soils are of local origin. In other words, where the soils are the product of bedrock that has been weathered in place. These soils are referred to as residual soils. If you have transported material making up the soils, any geochemical anomaly may be too dispersed to be detectable, or it may be removed some undeterminable distance from the source. Also, barren transported material may mask underlying anomalous residual soils. Transported soils are typically of glacial or alluvial origin, but may include windborne silt called loess, volcanic ash, and organic muck. None of these are likely to develop good geochem anomalies above mineralized bedrock. Here's a case where doing some homework may pay. If no information exists on the type of unconsolidated material in your target area, then some things to look for which might indicate transport are rounded cobbles, many different rock types in the soils, and rocks unlike bedrock in that area. To collect a good soil sample, be sure to dig through the organic material and get down as close to bedrock as possible. You can see the difference in color. This is the organic material, which is not very good for soil sampling. And then again, the residual soil. The soil which is really close to bedrock and probably contains fragments of bedrock in it. And basically, what you want to do is just fill this bag, again, so that you'd have about a coffee cup full, maybe 2 coffee cupfuls of that 80 mesh material. Because typically you'd run your soils for minus 80 mesh. As a practical matter, soils vary in thickness and development. In some places, you may not be able to get close to bedrock without an auger. In other places, there might not be much soil at all. Just use your best judgment to get the best sample you can.
If there's good outcrop to examine in your prospect area, it's important to take a careful look at it. Sediment geochemistry is great for narrowing your search area to a particular prospect, and soil sampling is important if that's all that's available. But we're looking for ore bodies in bedrock, so if possible, you will want to examine and sample the bedrock. Before we get started looking at rocks, let's review the concepts of alteration and mineralization so that we have an idea of what to look for. Remember that when you get into a mineralized system, what you're likely to be able to see are not the ore minerals themselves, but other evidence that a hydrothermal system was operating. There are 3 important things that you should look for. The first is silica. Silica, or quartz, is transported and deposited by almost all mineralizing hydrothermal systems. It can take the form of large veins or tiny veinlets, or it can replace host rocks chemically without any veins at all. This is called silicification, and it makes rocks harder than they would be otherwise. If you scrape your hammer or a knife across the rock and it leaves steel, chances are it's silica. In any form, hydrothermal silica is an important form of alteration. The second thing to keep an eye out for is iron staining. Iron is another very common element introduced by most hydrothermal systems. It is usually in the form of iron sulfide or pyrite. Pyrite is a light yellow metallic-looking mineral that often occurs as cubes. On the surface, though, it is usually weathered and oxidized to limonite, which is essentially rust, and is reddish-orange to brown or yellow in color. These colors will stain any rock that contains significant pyrite, and they're easy to spot. We should note that many rocks that are not altered contain significant iron and can weather to red and orange. But it's still a good idea to keep an eye out for iron staining and to investigate any suspicious red or orange spots. The third thing to look for is acid alteration. As we learned earlier, hydrothermal fluids are commonly acidic, and a common effect of acid alteration is the breakdown of feldspars, one of the most common rock-forming minerals, into softer clays or micas. The net effect is to turn a good hard granite or volcanic rock into a soft, punky material. In extreme cases, rocks can be turned entirely into clay, but in mild cases, only the feldspars will be affected, turning what was a bright, shiny, hard mineral on a fresh broken surface into a soft, cloudy mass. One of the tricky things about acid alteration is that normal weathering, acid rain, has very similar effects. So if you're in a very humid climate where the rocks are deeply weathered, acid alteration probably won't be very useful. When you get up to the outcrop, take a look at it for any signs of mineralization, veining, silicification, or iron staining. If you see anything interesting, take a sample. It's not important what the sample represents right now. We're not trying to define an ore body. We're just trying to get an idea of what the potential might be. Knock off a piece or several pieces with your hammer and put them in your sample bag. Tie it up, label it with whatever numbering system you're using, and toss it in your pack. Be sure to mark the spot and the sample number on your map so that you'll know where it came from. And it's a good idea to briefly describe the sample in your notes. How much you write down is up to you, but even something like iron-stained granite is better than nothing. In gold exploration particularly, it's a good idea to sample the rock even if you don't see anything that's very interesting. Alteration associated with gold deposits can be very subtle, even to the practiced eye, so the prospector shouldn't make the mistake of assuming that he can tell just by looking which rocks have gold in them and which don't. The fact that you have gold in the stream sediments draining the area is enough to justify sampling the rock. Often you'll be in areas that show evidence of old prospecting or mining. If you get into a situation like this, one of the first things to do is figure out what the old-timers were working on. Often the old workings are caved or otherwise inaccessible, so you won't be able to see or sample what they were digging on. You can, though, usually find something on the pile of material that was dug out of the hole and piled near the entrance. This pile is called the waste dump, and it represents the rock that was cleared out of the hole in order to get to what the prospector or miner was after. Most of the material that you find on the dump is likely to be uninteresting, but usually there's a scrap or two of the vein or ore zone that was left. This should be sampled. And a sample of the uninteresting waste material is often a good idea too. The old-timers sometimes missed low-grade mineralization if it was not in a vein or some other obvious form.
If old workings are open and accessible, you should examine and sample them. However, you shouldn't go underground without proper training and safety equipment. Getting into small prospect pits and shallow workings is reasonably safe if done carefully.
Keep an eye out for rattlesnakes or other critters that might have moved in, and don't hammer on any rock that might fall on you or trap you. Try to figure out what the target was and sample it. If a vein or other structure is exposed, a grab sample is okay, but a chip sample is better. For a chip sample, you take a series of chips across the vein, trying to get a representative sample of the whole vein. Put all the chips into one sample bag and make a note, such as 5-foot chip across quartz vein. Commonly, when you get onto a prospect, you won't see a vein or other discrete body that you can identify as your target. Often any veins will be small or low grade, or you might not see any veins at all. Your target is likely to be a larger, more diffuse zone that is not so easily measured or defined, like this entire hillside. It may be a zone of alteration or an area where you've gotten a cluster of good grab samples. Usually, the way to attack a problem like this is with a sample grid. You lay out your grid just like we showed you for soil sampling, and then you take a rock sample at every point on the grid. Chances are you won't have 100% outcrop, so you might need to leave some holes in your sample grid, or to move a sample point slightly to get a good sample. You might even want to take soil samples where the outcrop is covered. All of these things are fine as long as you take good notes and mark your samples on the map accurately.
Grid sampling does two things for you. It generates a statistically valid sample over a relatively large area, and it forces you to take samples from spots that you might otherwise have missed. In gold exploration, this is very important. Once you've located a prospect using surface geology or geochemistry, you may want to acquire the ground to try to market it. Sometimes it's unclear as to how much ground to actually acquire, or where the subsurface extension of the mineralized outcrop may be. Often rock around your discovery is covered by soil or alluvium. Here in the basin and range, the mountain ranges are commonly bounded by faults, and it's unclear whether the adjacent valley has shallow bedrock that might be prospective, or thousands of feet of gravel cover any possible extension to the mineral deposit. Usually, you just take your best guess and go with it. But it's important to know that there are other techniques available to you out there that address some of these questions.
Geophysics involves measuring physical properties of the Earth in order to learn something about what's down there beneath our feet that we can't see. There are three techniques that might be useful to you: gravity, magnetics, and electrical methods. The pull of gravity depends on mass, so gravity is slightly greater when you're standing over dense, heavy, solid rock than when you're over relatively light sand or gravel. Gravity is most useful for getting a rough determination of how deep the gravel might be in a valley. Most rocks contain magnetic minerals, chiefly magnetite, a strongly magnetic iron oxide that's the major component of black sand in your gold pan. Rocks that contain a lot of magnetite can actually draw a hand magnet, but even small amounts of magnetic minerals in rocks can be measured with sensitive magnetometers. Different rock types can be distinguished by their magnetic signatures and traced under soil or other cover using a magnetic survey. Generally, the most useful of the geophysical techniques in mineral exploration are the electrical methods. There are several different electrical methods, but they all involve measuring the response of the Earth to an imposed electrical field of one sort or another. A metal detector is actually an instrument that uses these principles. The targets of these methods are usually sulfide minerals such as pyrite, which is often associated with ore bodies, and other base metal sulfides that are ore minerals themselves. Sulfides are metallic in appearance, and they also behave physically much like metals. They're typically much more conductive than other minerals and more able to take on an electrical charge. Without going into great detail, the electrical methods can be very effective in discovering buried sulfide deposits. Unfortunately, they're also the most expensive of the techniques that we've talked about, and they require the most expertise in conducting and interpreting surveys.
If it looks like your project might benefit from geophysical testing, your best bet is to find a geophysical contractor and ask him for some advice. You might even be able to rent some of the equipment and run the surveys yourself. Finally, remember that geophysical data is available at the USGS and State Geological Survey libraries. It probably won't be very detailed, and it probably won't include electrical data, but it could be useful. And also, there will be people there to help you interpret it. There are other geochemical techniques that are being used instead of or with standard geophysical techniques to help you see through gravel or other types of cover. Talk to the labs to see if they can help you. Once you've collected your samples, you need to get them analyzed. There are many labs that do assays and geochemical analysis, and most of them are honest and competent. There are some, however, that aren't reliable. For this reason, the exploration industry relies on a few big, well-regarded labs for most geochem work. These include Bondar-Clegg in Denver, Chemex in Vancouver, BC, and XREL in Ontario. When it comes time to sell your prospect to a mining company, they'll take your analysis much more seriously if they come from a lab that is known and trusted. If you call the labs, they'll send you a catalog of analytical packages with prices and order forms to send in with your samples. They're also happy to provide advice if you're not sure what you need. Generally, you'll want a multi-element package that includes a very sensitive and accurate gold analysis, plus other precious and base metals and important indicator elements. Some labs routinely report up to 56 elements. Gold and a few other elements are usually reported in parts per billion, or ppb, and the remainder are reported in parts per million, or ppm. These units simply describe the proportion by weight of that particular element in the sample. Once you've decided that you have a discovery, you'll want to lock up control of the mineral rights. The first thing to decide is how big of an area you want. Generally, you want an area big enough to cover the suspected ore body, or at least the anomaly you've discovered in the soils. Since at this point you don't know the size of the ore body, you're going to have to use some judgment. As a minimum, you should acquire at least 320 acres, which is half of a square mile. The upper limit of the size you want is determined by the cost. If you have the guts of the ore body, you'll be in pretty good shape when it comes time to negotiate with a mining company. On federal ground open to mineral location, staking is the method for acquiring mineral rights. The federal 1872 mining law is the governing statute. However, each state is allowed to specify its individual staking requirements, so that staking procedures will vary from state to state. This makes it necessary for you to check in whichever state you're working what the particular staking requirements are. Most geological survey offices or mining offices in the state in which you're working will have this information. If you're not familiar with federal mining law, I would also recommend getting pamphlet 048, Mining Claims on Federal Land, which is published by the BLM. In general, a federal lode claim covers about 20 acres and is 1,500 feet long by 600 feet wide. To stake the ground, plot out your claims on a topo map. This will help you in the field to locate where each post goes. A string box will help you walk off the proper dimensions of the claim, and a compass is needed to keep your line straight. A post 3 feet high is erected at the four corners. The diameters of the posts can vary from state to state. Also, 2 posts are erected at the midpoint of the end lines. These are the centerline posts. A discovery post is also needed. The discovery post is located within the boundaries of the claim, somewhere along the imaginary line between the 2 center inline posts. Attached to the discovery post is a pill bottle or some type of container in which the location notice is placed. The location notice contains information which identifies the owner, claim name, date of location, where the claim is situated, and a map showing the claim in relation to its surroundings. Standard fill-in-the-blank forms are available for location notices, and the map is generally a copy of a USGS topo map with the claim sketched on it. From the date of location, you have 90 days to record duplicate copies of your location notice with the county recorder's office in the county in which your claims are located and also at the BLM office. Failure to do so will invalidate your claims. Recording costs with the county recorder will vary, but generally are around $10 per claim. Federal recording costs are more significant. It costs $35 to record plus $100 for the first annual rental payment. A rental payment of $100 is then due to the federal government every year on or before August 31st to keep the claims valid. Mineral rights can be acquired on state land by either staking or leasing. To find out the particular details for this procedure, you'll have to contact the state land department in whichever state you'll be working. At any time after you've acquired the mineral rights to your prospect, you can begin the process of marketing it. There's always a question, though, of how much work to do before selling. That's a tough question, since it depends on your means, your confidence in the prospect, or your ability to enhance its value by doing further work. If you choose to do further work, it means more money out of your pocket. However, the payoff may be bigger once you make a deal. For most prospectors, it's probably best to sell as soon as you've put together a package that will attract a mineral or exploration company. In order to sell your prospect, you need to put together a report describing it. The report doesn't need to be fancy, but it should be neat and well organized. It should include maps showing the location and boundaries of the property along with your sample data. A short written description of the property should accompany the maps. After you've prepared a report on your prospect, start getting in touch with mining companies. You'll probably want to lease, option, or sell the property outright. If you're lucky, the company that you've struck a deal with will advance the prospect and it will eventually become a mine. In this business, the companies that you'll be dealing with will fall into one of 2 groups. 1, major exploration and mining companies, and 2, junior exploration companies. The majors are big, well-established companies that have been around for a while. Companies like BHP, Cominco, Kennecott, Newmont, and Placer Dome fall into the first group. Junior companies are much smaller and less established. Often, they don't even have a mine. They're looking for their first one. The juniors are mostly Canadian companies listed on the Vancouver and Alberta stock exchanges. Most of the companies that you'll be dealing with have offices in Denver, Reno, Vancouver, or Toronto. A check of the yellow pages in any of those cities will provide you with a long list of potential customers. They may even have field offices closer to where you live. If at all possible, make a personal visit to a company's office. It's a much better approach than a phone call or just a letter. It gives you an opportunity to present your data package and even show off some rock samples. Good rock samples are worth 1,000 words. But call first to make sure that you can set up an appointment. You may want the company to sign a confidentiality agreement before looking at the property or reviewing your data. The agreement should include an area of interest, usually anything within 1 mile of your property boundaries, that is protected. If the company reviewing your data should stake any ground within 1 mile perimeter during the stipulated period, normally 1 year, it's treated as if it's yours. This is standard practice. Unless the company is already working in the immediate area, it shouldn't be a problem. Most companies have a standard confidentiality agreement that could be used for your property. If a potential buyer comes to examine your prospect, he should be allowed to collect a reasonable number of samples to confirm your work. But unless you feel it's in your interest, additional work should not be done unless you have a contract. Also, any data generated from your prospect should be immediately available to you. Also, don't agree to hold any data confidential for more than a few weeks. Let's talk about deals now. There are two main choices, a straight lease agreement and an option to purchase. Remember, this is a free market system. There really isn't any set price. You try to get the best deal you can, and so do the mining companies. But there are a few things that I can suggest that should be in the contract. In a straight lease agreement, you should get a payment on signing and an annual rental payment each year on or before the anniversary of the signing. The company should also agree to cover all costs of maintaining the property so that all claims or permits stay valid. The yearly rental payment should escalate to make it expensive for the company to just sit on the property. And a work commitment is also a good idea. This requires that they spend a certain amount of money every year exploring your property or paying you additional cash for the difference. For a raw prospect in the current market, the signing payment should be around $10,000 to $25,000 and escalate to $100,000 within 5 or 6 years. Work commitments should be at least $100,000 annually. The last important element of the contract is the royalty. Royalties are typically set as a percentage of the net smelter return, the NSR. The NSR is the amount of money that a mining company receives from the smelter in payment for the ore or concentrate sold. It approximates the company's total revenues from mining on your property. A typical NSR royalty these days is on the order of 2 to 4%. On a 1,000,000-ounce gold deposit, that's a pretty good chunk of change in your pocket. So don't be too hard-nosed about it unless you have something really hot and a lot of companies want it. In any agreement, the company will be allowed to turn the property back to you and terminate the deal at their option. An option agreement is similar to a straight lease, but it gives the company an option at some point to buy you out completely and terminate annual payments, either including or excluding the NSR. Again, the buyout price is whatever you can get. In some cases, with juniors in particular, they'll offer you stock in their company instead of land payments. Some stock is all right, but you should get cash with it. Finally, I would suggest getting a lawyer who's familiar with these sorts of deals. It will cost you some money, but you're better off paying a little up front than making a bad deal. Well, that's about it. The rest is up to you. If you find the big one, you can retire on the royalties or go out and look for the next one. Remember, work smart, not hard. Good luck to you and good prospecting.